All right, so here's a nice little problem that involves looking at some multiple point charges and the potential differences in the vicinities. So here's the problem. All right, so we've got ourselves point charge, Q1, which is 3 microcoulombs, and it's at the origin of a Cartesian coordinate system. So we can draw up a little system here. We've got ourselves a nice little Q1 here, which we will use for Q1. There we go, got its charge. And we want to know what is the potential difference between 2 points. So we're not told what those 2 points are yet, but let's say that point A, say piece of A. Point A is, let's say that it is 30 meters. Piece of B is equal to 2, 5. So we want the potential difference between those 2 points. So A, we want delta V, piece of A to piece of B. All right, so let's just go ahead and get this, right? Let's draw in these little points here. We could say 1, 2, 3, 1, 2, 3, 4, 5. And we've got piece of B's there, piece of A's there. Piece of A, piece of B. There we go. So we got those 2 points, and we want to know what is the potential difference between those 2 points. Fantastic. Well, we got this nice electric field that's radially outward. Do we need to draw it in? We do not. We do not. We just got to figure out how far away are we from this charge, being point A and point B. So we've got this, right? We've got some R1A and some R1B. We'll call it. The radial distance is away. That's all that we need to know. Right? So how are we going to get those radial distances away? Well, R1A is just going to be equal to 3 meters. It's just from the origin to this. R1B is going to be gotten by a little bit of triangulation, right? It's the hypotenuse of the triangle form that goes over 2 and up 5. So we'll get the R sub B is the square root of 2 meters squared plus 5 meters squared. We've got root 29. Fantastic. So what do we get then? Well, we've got the potential V1A, the potential at point A due to Q1 is equal to K sub B times Q1 divided by R1A, which is then equal to K sub B times 3 microcoulombs divided by 3 meters. And then V1B is equal to K sub B Q1 divided by R1B, which is K sub B times 3 microcoulombs divided by root 29 meters. All right, so what do we get out of this? Delta V, PA to PB, I'm writing these a little different every time. PA to PB for points is going to be equal to B minus A, right? V1B minus V1A, which is going to be equal to K sub B times Q1. I can factor that out because it's a common term to both of them. And then we've got, this is 3 microcoulombs. 3 microcoulombs multiplied by 1 divided by root 29 meters minus 1 divided by 3 meters. All right, so we go ahead and check this out, right? Let's do it. So we got 9, 9th, 3, 6, 6 times 1 divided by square root 29 minus 1. Get negative 3,982 of this column. Delta V, piece of A to piece of B is equal to 3,982. Yeah. Well, let's call it 981.7. Oops, 981.8. My bad. There we go. So there's the potential difference. Does that make sense? And it turns out to be negative, number 1. And the answer to that is, well, is R1B, is point B further away or closer to the charge under consideration than point A? Yeah, this is a greater distance than this, right? So B is further away than A. So if we're going from A to B, we are actually moving radially outward. If you're moving radially outward in the vicinity of a positive point charge, then you are moving in the direction of the electric field. You're moving in the direction of the electric field. You are moving through a negative potential difference. So yeah, that's right. There we go. Pretty big. That's okay though. There we go. So fantastic. Now what we're going to do is we're going to say, let's take a charge. Let's take a charge Q2. We're going to say that Q2 is equal to negative 5 microcoulombs, and we're going to move it from PA to PB. Move from PA to PB. We want to know what is the change in potential energy in doing so. So we go ahead and stick the charge there. We're not worried about putting it there. We're worried about what happens when we move it from point A to point B. It's the change in potential energy of the system. So do you think it's going to increase the potential energy or decrease the potential energy? You say that, well, we're moving it through a negative potential difference, right? That's true. That doesn't mean the change in potential energy is definitively negative. It depends on what charge we're moving. If I were to take a negative charge here and I'll let go of it, which way does it want to go? It's attracted to this positive charge, right? It wants to go that way. And if it goes that way, it's losing potential and gaining kinetic if only the electric field's acting on it. The further we are away with a negative charge, the more energy that's stored in the system. So if we're going from closer to further away from this charge, and that charge is negative, we should be gaining potential energy, increasing the potential energy of the system, because we've got to physically move it back. The electric field doesn't want it to go that way. The electric field wants to pull it in towards this charge. We've got to pull it back. So we've got to put some energy in, and the electric field does negative work. At any rate, we've got delta PE, and moving Q2 from PA to PB will be equal to Q delta V. Q is the charge that we're moving, which is Q2, times the potential difference that we're moving it through, which is the potential difference due to Q1 between those 2 points. So we've got this. It's delta V PA to PB, which is then equal to negative 5 microcoulombs multiplied by negative 3,981.8 volts, which gives us times 6 G times, not divided by, we got about 1.991, 0.0, let's call it 1.991 times 10 to the negative 2. 1.991 times 10 to the negative 2 joules. Increase the potential energy, positive, as we said that should definitely be the case. So now what do we have? Now we have this. We've got ourselves a Q2 right there at point B. Does that change the potential at other locations? Heck yeah, it does. Now we got 2-point charges. So what could we say? Say, well, what is the potential at point A now? Or we can pick any other spot. What's the potential at point C? Wherever we want, really. I'm just going to pick point A because it's the easiest thing to pick at this point. Now, what is VPA? Well, V sub PA is going to be equal to V1 at point A plus V2 at point A, which is going to be equal to K sub E, Q1 divided by R1A plus K sub E, Q2 divided by R2A. Well, this is what we got to be a little bit careful of, is R's here. R2A is not the same as R1B. R2A, the distance from charge number 2 to that point, P sub A. So we need to figure out what that is. And again, we've got a little triangle here we can make. The hypotenuse of that triangle, we've got a base of 1 and a height of 5. So we've got the R2A is going to be equal to the square root of 1 meter squared plus 5 meters squared, which is root 26 meters. All right, so in the end, what do we have? We've got a K sub E times 3 microcoulombs divided by 3 meters plus K sub E times negative 5 microcoulombs. Don't forget the negative sign, it's a negative charge there, divided by root 26 meters. So what do we do? Go ahead and compute this out, and we've got ourselves 0.99 to the ninth multiplied by the quantity 3 e to the negative 6 divided by 3 minus 5e to the negative 6 divided by square root of 26. Looks good. 174.6 we'll call it. There we go. There's the potential at point A now due to both Q1 and Q2. What else could we do now? Well, we could put up another point charge at this and move it between 2 locations. Say, what's the potential difference that it moved through? What's the change of potential energy? All sorts of things. I'm going to start doing more and more and more. Hopefully this kind of gets us on track for just being able to treat point charges. And ultimately define the overall potential at a given region in space and associated with changes in potential energy of moving charges. Whew. All right, all charged up. Whew. High potential. Have a good one. See you next time.